We're going to look at a reversible liquid phase reaction in an isothermal CSTR. However, instead of being given the rate constants, we're given the conversion for some flow rate that we don't know, and we want to know what's the conversion if we increase the flow rate by 50%. We're also given equilibrium information, and so we can use this information to determine the new conversion without actually knowing the rate constant or the volume of the reactor or the volumetric flow rate. We just know that they're not changing when we increase the flow rate. So let's first look at let's write down the reaction and draw a diagram showing the information that's known. So the rate of reaction for A, it says it's first order in A and first order in B. It's the Ford reaction. The reverse reaction is second order in the concentration C. Now the problem tells us that equilibrium conversion is 0.80, which means this is when the rate of reaction is 0. That's what equilibrium corresponds to. So the rate of reaction is 0. That means K1, the concentration of A now, is 0.2 times the inlet concentration. Likewise for the concentration of B. And the concentration of C, so when 1 mole of A reacts, it makes 2 moles of C. So that means 0.8 moles per volume, 0.8 moles of A react. We're going to make 1.6 moles of C. So concentration of C is 1.6 times the feed concentration of A, and that's squared since it's second order. And so we can just simplify this equation. Let me pause and do that. So we know the rate constant for reaction is 64 times rate constant for the reverse reaction. So now what we want to do is write down a mass balance on A, and we're going to do this with the case where 60% conversion, that's our initial condition. So mass balance says the molar flow rate in, so moles per time, molar flow rate out, plus rate of reaction. Those should sum to 0 if we're at steady state. And now the molar flow rate is the volumetric flow rate, which is constant, and times the concentration coming in, Ca0. Volumetric flow rate's the same, leaving. If we're 60% conversion, then the concentration of A leaving is 40%. And then we can substitute in for the reaction rate. So minus K1. Ca leaving, we said, is 40% of that entering. Likewise, since the concentration of A and B is the same, this is 0.4 Cb0, which is the same as 0.4 Ca0. And then the reverse reaction, if 0.6 moles of A react, we make 1.2 moles of C. So this is 1.2 Ca0, and it's second order, so that's squared, times the volume of the reactor. And now let's simplify this. I'm going to pause and simplify. And so we can cancel out one of these Ca0 values, and then we can replace K1 by 64 times K2. So I've done now, I squared the terms. We can simplify this further by factoring out K2 and then calculating the numerical value. Well, it's going to move the 0.6 V0 to the left side of the equation. So I can rearrange and solve for ratios of constants. We don't know rate constant, feed concentration, reactor volume, or volumetric flow rate, but we know a term that includes all those, so just rearranging this equation. So then we're going to write down the mass balance again. The only change is the new flow rate. So V2 is 1.5 times V0. And otherwise the mass balance is the same. So let me rewrite that mass balance. Now here, in order to solve I'm going to write this in terms of conversion, and for a constant volumetric flow rate, we're at steady state and the inlet and outlet volumetric flow rates are the same, then X is equal to this. And keep in mind that CA leaving the reactor is the same as CB, because CA and CB entering the reactor is the same and we're at steady state. Also, the concentration of C, if we have a conversion, concentration of C leaving the reactor be 2x times what that feed concentration of A is. So I can substitute in for these variables, and let me just stop and substitute in to the mass balance. So I've made the substitution where, note I also substitute in K1 as 64 times K2, and CA is CA0 times 1 minus X, which of course is also CB for this particular case. So now I'm going to substitute in this value that we calculated, since K2, CA0, V, and the volumetric flow rate are the same for this new condition. And now I'm going to divide both sides, both terms I should say, by 0.0682 and simplify. And this then becomes multiply, take everything to the left side. So I can use a quadratic equation, and I just use a app on my calculator for quadratic equation, and I get x equals 0.546, which would round to, so conversion 55%. Of course, there's two roots to the quadratic equation. The other root's greater than 1, so it's not physically meaningful. And then we can check, because we had a conversion of 60%. We increased the flow rate. We expect the conversion to decrease, and indeed the conversion decreased.